Good morning, everyone. Stop talking and start listening. Come on, people. Shriya. Morning. Welcome back to our regular seminar, the one to be given today by Murat Uzundag, with a focus on evolved compact pulsators. That's hot subdwarfs and white dwarfs, for those who didn't know. Murat did his bachelor studies in Turkey, I believe, and master studies Turkey and Poland, right? Yeah. Then he moved to Chile to complete his PhD with Maja Vukovic, I believe, former postdoc here, I think, with Connie. And then he joined us in 2023 as a junior FWO postdoctoral fellow with a focus on compact pulsators. And that's what we are going to hear about today. All right, Murat, the floor is yours.
Thank you, Andrew, for introduction, and thank you for coming. Today I'm going to talk about the final stages of stellar evolution, and from the asteroseismological point of view. And I will focus on two types of stars, hot subdwarfs and white dwarfs. And I will review what we have done last over decade, and especially the works that are involved. And let's start where we're going to concentrate on today. So here is the HR diagram for all pulsating stars. So here is the dashed region, and as you can see here is where the hot subdwarf B stars are located. And three instabilities, this is the white dwarf cooling stage that we will focus on. So as you can see here, it's really beautiful that there are many instabilities that which enable us to probe the interior of these stars and understand better how these stars evolved and get the final shape in this late stage of stellar evolution. And one of the most remarkable results came from the Gaia. So before Gaia, we knew that a few thousand hot subdwarf B stars, and from the different surveys, and there was several difficult selection effect. And now we have around 60,000 hot subdwarfs, which is great because we can create different types of samples and selection criteria that we can apply, and we can try to do nice science cases using these beautiful data sets. In the case of white dwarfs, it's even much better because now we have around 400,000 white dwarf candidates, so which is amazing. So let me introduce the hot subdwarfs, and so here is the color magnitude diagram from Gaia, and hot subdwarfs are located in this region, so they are the subdwarfs and below the mean sequence, and they are the much brighter than the white dwarfs, and they are hot because, and as you can see, the effective temperature around 20 to 40,000 Kelvin. So if you consider the progenitor of hot subdwarf is a low mass mean sequence stars. Once the hydrogen is depleted in the core, the core is start to shrinking while the outer envelope is start to expand, and the star is moving towards the red giant branch phase. Here is the critical stage to form extreme horizontal branch stars, which are hot subdwarfs, because the star before or during the tip of the RGB phase must lose almost all hydrogen envelope from the surface, and what is remained is just naked core of low mass red giants, which is going to be located in this range, which is the mass half of the sun, and it has a convective core in where the star start to burn helium into carbon and oxygen, and top of that it has a helium mantle, and on top of it really thin hydrogen envelope. And as you can see here is this is more or less half of the sun, and the radius is around 10 to 30% of the sun. And after this helium core burning, which takes around 10 to 8 years, once the helium is depleted in its core, the star, since it has no hydrogen envelope, it's unable to ascend through the asymptotic giant branch phase, but rather it's going directly towards the first STO phase. It's not working now. And then white dwarf cooling stage directly. So one of the biggest questions is that how a star can lose almost all hydrogen envelope from the surface during the red giant phase. And one of the best way to explain this is the binary channels. And there are two mechanisms have been proposed to form hot subdwarf P stars. The first one is Roche-Lobe overflow channel. And this is the channel that I'm showing you here. So the stars, it's, in this case, the mass accretion is rather stable. And then what is remaining after these red giant phases, and the orbital separation increases due to the accretion. And what is remained is the hot subdwarf P stars, which is a really long orbit, around 500 days up to 1,600 days, with the main sequence stars, which can be FGK type. And other two channels, as you can see here, explain the short period systems, which is STB plus either M dwarf or white dwarf. And depending on the initial mass, it can be going through the just one unstable Roche-Lobe overflow, then the common envelope, or unstable Roche-Lobe overflow, and just the one common envelope. Then what is remained is the STB with the main sequence stars with the 0.1 to 10 days. And at the moment, we know around a few hundred of these types of objects. And these stars are really difficult to find, as you can see, because it's the orbital separation is too big. But there was a former PhD student in Leuven, Joris Vos. He dedicated surveys. It shows around 26 systems at the moment that we have. So current consensus is that we need always perhaps binary interactions to form these types of stars. And these two channels creates around 60 to 70% of all populations. And it seems that there are 30% or 1/3 of the population seems to be single. And for those single STBs, two channels have been proposed. One of them is two helium white dwarf stars merged each other, and what is produced is half of the sun with the core helium burning star. And the other potential option is that if there is a close substellar companion during the tip of the red giant branch phases, that might be responsible for removing all the envelope from the surface of these low mass red giants. But later study shows that, and the numerical calculations show that that might not be the case, because this ejection is, or the removing all the envelope from the surface, this substellar companion might not be enough. So, from the pulsational point of view, and there are two kinds of pulsating hot subdwarfs, and the upper panel that I show you, short period pulsating hot subdwarfs, which is order of few minutes, and amplitude is much higher than the long period STBs with the few magnitudes. And in the bottom, red ones are the long period STBs with the order of a few hours, and which makes them pretty difficult to detect from the ground because, due to their long period. And if you look at from the T-effective log-G diagram, these short periods, which are associated with the pressure modes, which are sensitive to the envelope properties of these stars, located in the higher effective temperature range and the higher log-G. And while the long period STVs, long ones, these modes are associated with the gravity modes, which are probe the deep interior of the stars and the core conditions of the stars. And those are located in the lower log-G and lower effective temperature range. And in between, there are hybrid stars that shows PNG modes at the same time, which are quite nice objects because that allow us to probe both envelope properties and the core properties of these stars. So, concerning what would be the pulsations occurrence rate concerning these stars, and if you look at the P mode region, and the previous study shows that the pulsation occurrence rate around 10%. While if you go to the lower effective range in the gravity mode instability, the occurrence rate is increasing up to 75%. But these are the all numbers, as you can see. So at the moment, we're trying to fine-tune this number. And to do so, I made a dedicated study. So first, I collected all known pulsating STBs from the literature. So here is the all potential hot subdwarfs from the literature, from the Gaia DR3. So just I overplotted all known pulsating STBs. And here is this blue region is basically the empirical instability strip where these stars are located, which is really nice because now we know that where to look to find these types of objects. And there are, as you can see, beyond the 0.1 GPRP range, there are some scatters. These are mostly composite STBs. So STBs, pulsating ones with the FGK type binary companion. So from TESS and also combining with the low-resolution spectroscopic follow-up from the ground, including NTT, SOAR, and also DuPont telescope from Chile, at the moment we characterized around 200 of them. And other 200 still we need spectroscopic data. But here is the current stage. As you can see, here is the evolutionary tracks between 0.46 to 0.48. And all these pulsating ones, how they distributed. And there are red ones, and still we don't know if they are binary or pulsating. So still we're trying to resolve using TESS. And one of the study also, Gaia currently, as you know, present light curves, right? And Princey, a few weeks ago, he presented his work in here in detail. So we applied machine learning algorithms to the Gaia data to characterize all the variables for these 61,000 objects. But a few thousands have light curves, and we found around 80 new systems. And one of them I'm showing you upper panel. So these are the binaries, ellipsoidal ones, or the eclipsing ones. And the lower panel that I'm showing you, the pulsating ones. These are also, we verified with the TESS. So, and Prince now trying to do multicolor photometry to identify the modes, whether dipole or quadruple modes. So, another work that we have been done, we tried to characterize all hot subdwarfs within 500 parsec volume-limited sample. This is important because, as I told you before, 1/3 of the population seems to be single, and 2/3 of the population come from the binary channels. But this number has to be well constrained to test the binary population synthesis. So to do so, we observed all STBs within 500 parsec and characterize all of the stars in this volume-limited sample. And as you can see here, I just summarized what we have within 500 parsec so far. And around 178 STB stars, 65 STOB, 32 STO, and 30 helium STOB. These are just spectral type. If you have a hydrogen-Balmer series, basically you have STBs. And helium lines, depending on the strength of the helium lines, you can classify STO or STOB. So one of the key findings in this study, the space density of hot subdwarfs is an order of magnitude lower than the predicted one from the binary population synthesis studies by Han et al. And this is, of course, is a problem because discrepancy suggests that either a significant population of hot subdwarfs remains undetected, or fundamental aspects of binary evolution and mass loss not fully understood yet. So, or it can be both. So still, we are doing follow-up observations from Chile and from Canary to characterize all STBs within 500 parsec to find an answer for these important questions. And also, my focus is that what would be the occurrence rate of pulsations once we characterize all these STBs. So at the moment, combining with my findings, so we have around 400 stars pulsating ones. And when I clean all the stars up to 500 parsec, it seems that regardless of the both instabilities, G and P mode region, the pulsation occurrence rate 12.5%. But this is just a preliminary result. So from the asteroseismological point of view, and space missions dataset, especially from Kepler, was extremely useful to identify the pulsational modes. And one of the methods is that rotational multiplets. And as you can see, and non-radial oscillations, as you know, it's characterized by three numbers, N, L, and M. And these azimuthal orders equally spaced in the frequency domain. And this is proportional to the rotation period of the star, right? And in the case of, I'm showing you dipole mode, so it's equally spaced in three components, M equals 0, 0, 1, and plus 1. And the upper one is the quadruple modes, and nicely spaced with 5 components for one of the STB that have been observed by Kepler, the Kepler Space Telescope. Another method is the asymptotic period spacing. So basically, in this method, all the modes are equally spaced in the period domain. And what I'm showing you here is the one star from the TESS mission. And all these modes are equally spaced, and the dipole modes are showed by red dots. So each 250 seconds, there is one pulsational mode that equally spaced. And then if we fold up here, as you can see, there is a nice ridge. If you assume that these stars are homogeneous, so what you should see is a straight line that just located at 0. But as you can see here, there is this scatter around the 0, because these stars are chemically stratified. And if you modeled these objects, you can get nice information where the core helium burning is, what is the actual limit of the core helium burning, or what is the size of the core of these objects. So this study has been done for 40 stars. So I made an analysis during my PhD. So I collected 40 stars that shows several pulsational frequencies that allow me to identify the dipole sequence. And what is really important, we test 2 assumptions. One of them is we applied for the models a strict Schwarzschild criterion. So this is basically the lowest mass that burn to helium into carbon and oxygen. The other one is we include some convective boundary mixing. So the mixings are, as you know, that is important. And one of the work that Hamed Ghasemi showed that inclusion of the mixings are extremely important. And this was also the case. So we proved the assumption 2, so which is extremely important because this is the period spacing that we get between 280 to 230. And if you assume just a strict Schwarzschild criterion, all the models are failing, as you can see here. But if you include some mixing, that's representative what we observed, so which is really nice. And this was one of the seismic conclusion for these stars. So let me talk about a little bit white dwarfs as well. So white dwarfs are the final stages of around more than 95% of all stars in Milky Way, right? And therefore, they are quite fundamental in our understanding formation and evolution of stars and the planetary systems. So there are basically two main gradients of white dwarfs, hydrogen deficient ones, which corresponds to around 20% of all population, which this result comes from, by the way, STSS. And a vast majority is 80%, which are hydrogen-rich enveloped. They have hydrogen envelope, and which we called DA. So this is the three main instability strip, by the way. So there are two instabilities, including the hydrogen deficient ones, DOVs and DBVs. So by the way, D stands for degenerate O-type variable. DBV is a degenerate B-type variable, and DAV is the degenerate spectral A-type variable. So here is the spectral window of white dwarfs. So here is the DOs, the hottest ones, and shows some carbon and oxygen lines. DBs show strong helium lines. DAs shows hydrogen lines only. And DZs, these days these stars are quite important because it shows some heavy elements on the atmosphere of white dwarfs. And as you know, the white dwarfs are extremely dense objects, and whatever you put on the atmosphere of white dwarfs, it should sink within a few hours or within a few days, depending on the T effective. All these heavier elements, rather than hydrogen and helium, should immediately sink out. But we see some heavier elements, so that indicates the recent accretion from the planetary remnant around white dwarfs. So there are DCs. DCs are, there is no any line. So these are basically crystallized white dwarfs. So there is no any atomic interaction in the interior of white dwarfs. So we see these ones. DQs are the magnetically strong. These are high mass white dwarfs. So if you look at the mass distribution of white dwarfs, all of course, considering the Hubble time, the mass is located around 0.6 MSun, so in this range. And there are two tails, as you can see. And this lower mass range, there are extremely low mass white dwarfs. So if you consider the age of the universe, you shouldn't be able to find any star in this range, right? Because these are too low in mass. So therefore, these only can be produced by the binary interactions. And in these ranges, there are high mass and ultramassive white dwarfs, which I will also today mostly I will focus on these objects. These are interesting because the origin of these objects are unknown. So it can be either single intermediate mass stars can be formed and located in this mass range, or these are the merger products, which are important because these are supernova type 1a progenitors. So let's go through the instabilities. So there are three main instabilities. So let's focus on the first one. DAV is the most populated ones. So at the moment, we have around 500 of them. So they show basically non-radial gravity modes, which are excited by the convective driving mechanism. And TESS was extremely useful concerning these objects because we find several of them, and one of them I involved that we reported in a single paper 74 of them, which was a record. And as you can see, here is the evolutionary tracks corresponding to different masses. So here is the high mass region. So here is the 0.6 that's peaked around here, and here is the low mass, so where the extremely low mass white dwarfs are. Oh, something is wrong here. Okay, let me explain you what I want to show here. So in that slide, just I want to focus on this range, okay, to just extremely low mass white dwarf range. So at the moment, we are working on to characterize all of them using TESS data. So we have 36 of them. So what we're trying to do is detailed seismic analysis with Leila Calcaferro from La Plata group. So we're trying to characterize all these objects in this range. So concerning the ultramassive white dwarfs, we have just a few of them. And any findings concerning these objects are extremely important. And at the moment, we have just a few pulsating candidates. And recently, we have found the richest pulsating ultramassive white dwarf using the GTC. And I would like to note that these stars are extremely dim, like around G magnitude 18 to 22. So it's really hard to detect, and TESS pretty much useless for these targets, basically. And here what I'm showing you is the 5 different colors that we observed during the night. The observation length is around 6 hours. And here is the beautiful pulsational spectrum of this object. And as you can see, here is the nice gravity modes, all are. And we couldn't do detailed seismic analysis concerning these stars. We just derived the masses based on the evolutionary tracks. So based on the, there are basically 2 models that have been available, because, as I told you, the internal compositions of these stars are also unknown, because they can be formed either carbon and oxygen core or oxygen neon core. So using the evolutionary tracks, we find, if we assume carbon oxygen core, we found 1.14, 1.15 M-sun. And if you assume the core harbor by oxygen and neon, we have 1.12 and 1.14 M-sun. So, and we also derived what would be the, actually in future, because as I told you, the detailed period-to-period fit modeling using the asteroseismology, we cannot make it because at the moment we have no carbon-oxygen models, which is still in progress. And in future study will be extremely important, this object, basically. Another object that we found, which is the most massive pulsating white dwarf, which is around 1.3 M-sun. And for these stars, we did a detailed seismic analysis using the data from 3 different telescopes, from New Technology Telescope, UltraChem, Gemini, and Apache Point Observatory Telescope. So using these 3 telescopes, we extracted 13 significant pulsational modes. And here is that what I'm showing you, we derive just the mean period spacing. And here is the residual. And as you can see, here is the trapped region there is. And most likely it corresponds to the one transition region in the star. But we need to do so, we need to know, we need a detailed modeling. So using this period spacing for dipole and quadrupole mode, basically we derive the mass of this white dwarf. And also tentative rotation period is 0.3 to 0.67 days. And I forgot to tell you, and this star is, there is one candidate, and the rotation period is around 18 minutes. But this is just a candidate because since it's a ground-based data, it's aliases is a big problem for these objects to derive the real rotational period of these objects. So now let's go through the helium-rich white dwarfs, so DBVs, in the intermediate region. So anyway, they are similar properties of the STBs because they are just the vicinity, but of course the structure is completely different, and they show but the mechanism, heat engine mechanisms, so for both objects. And one of the problem is if you go to the edge of this region, is the models seems to be failed. So we need still detailed models to represent what would be the real instability strip for these stars. And concerning this region is we have around 50 pulsating members concerning these objects. And one of the famous one that we studied, which is the GD358. So this is the single TESS data set. And also this star is studied a lot in the literature based on the grant-based data set. And the whole Earth telescope, so the different region of the Earth world, they try to observe this star. But TESS shows amazing amplitude spectrum, as you can see here. So we found tens of pulsational frequencies, and again, we drive the mean period spacing for this star, and using the evolutionary tracks and the detailed asteroseismic modeling, we determine the mass of these objects. And here is the basically parameter space that we get. So here is basically, I'm summarizing the power of the asteroseismology. And we did some comparison with the literature also. So DOVs, these are the hottest pulsating white dwarfs. And here is the T-effective temperature range, 75 to 250,000 Kelvin. This is it's one of the most complicated region in the HR diagram. But these stars are quite important because after the asymptotic giant branch phases, these are the fresh product. And if you probe these interior of these stars, you can get an idea what happened in the previous stages, which is the least known stellar evolutionary stages, right, in the asymptotic giant branch phases, basically. And at the moment, we have 25 pulsating candidates. So in total, I think we have around 50 to 60 stars in this range. And the efficiency of the instability strip, so the pulsation occurrence rate, is around 50%. So this is two new discoveries from my PhD thesis, basically. So the TESS observed these two stars. And what I'm showing you here is the amplitude spectrum. And we apply the Helios 1 and dipole and quadruple mode sequences to derive what would be the potential pulsational modes for these stars. And then derive the basically mean period spacing, again, as in the case of DBVs. So we trying to determine the mass of these two objects. In the first case, we drive the dipole mode sequence, and the second case, quadruple mode sequence. And it also gives us what would be the evolutionary stage of these stars and the mass of these stars. And here is one of the stars that we did detailed seismological analysis, and here is the core composition of these objects. So the core through the surface of these white dwarfs, basically. So as I showed you, several studies that we made during last decade, but we want to test if what we are doing is correct or not, because there are some cavities. So in this study, we're trying to show what would be the potential problems in terms of, so what would be the potential cavities concerning these stars. So basically what we did is we measured all the seismic mass, and we compare with the spectroscopic and the photometric ones. So if there is a good match, 1-1, so what we do is basically is pretty good. But if not, it's something is wrong. And in this paper, it's a pretty long paper, and we really discussed all the potential problems. So one of the issues is that perhaps is the atmospheric models. So perhaps the T-effective and log-G, it contains some intrinsic problems. And the seismic models are not good, perhaps. Or another problem is that these stars are intrinsically faint. That's put some limitation to detect more modes, because as you know, if you have more pulsational modes, you have better models. If you have no, it's lower, worse models that you have. So I'm showing you it's just the DAV stars, and as you can see here is the spectroscopic versus astrometric masses, seismic masses versus astrometric masses, spectroscopic masses versus, again, the astrometric ones. So in this case, seismic ones, sorry. We got a really nice agreement up to 0.75 MSUN, and beyond that, we have scatter. So our models basically works pretty well up to this range. But beyond that, we have some significant scatter. But of course, as you can see here, it's maybe there is low number statistics as well, right? And also, similar study we did for DBVs and GW virgins or DOEs. And we found, again, the similar problems. But those samples even smaller than the DAVs. So these were the studies that we made last few years. And future, first of all, concerning the hot subdwarfs, at the moment we have around 200 objects to be observed because we know that those are variable. Either it shows pulsations or variability due to binarity. But we need spectroscopic data for those objects. And perhaps in future, SDSS 5 and foremost will be extremely useful for those objects. And another thing is that using the multicolor photometry, we can do now mode identification perhaps better, and also compare with what we get from the space missions. And what is remained to be done is, of course, the completeness of the sample concerning both volume-limited sample and pulsation occurrence rate. But this study will take some time, I think. Of course, once you define this thing, then you will be able to test the efficiency of the driving mechanism concerning pulsating STBs. And also, we will be able to define the boundaries from the observational point of view so that we can produce better modeling for these objects. Concerning white dwarfs, so since these objects are intrinsically faint, the TESS has some limitations, and most of the bright ones, we already did detailed seismic analysis. But now we need a bigger size of telescopes, such as GTC, or ultracam even can be useful for these objects. And there are several subtypes of them, which even I didn't touch these polluted pulsating ones, which I'm also working on them. And also there are interesting case that DQEs. So one of the lead study shows that these stars also might be pulsating. If it is the case, so then there is another instability, which is great. And we found now one of the good candidates, so it seems to be pulsating, so which we will present soon, I think. So, and for concerning hydrogen deficient white dwarfs, we need to revise the atmospheric models because there is a strong mismatches, and that we need to be corrected, basically. And also, astroseismic models should be revised for concerning high-mass pulsating white dwarfs. And also, so now still we have no carbon-oxygen core models that has to be made soon to test these high-mass pulsating white dwarfs. And that was all for today, and thank you very much.
Thanks, Murat, for a very enlightening talk. Time for questions, and we have plenty of time. Don't be shy.
Thanks, Murat. I have two questions, if I am allowed. So the first one is about the first part of your talk with the subdwarfs. I was wondering if you, because you mentioned that you do have some spectroscopic follow-ups and spectroscopy, observations, right? And I was wondering if you have noticed any specific chemical signatures which can give you some idea about possible binary interaction.
From the spectrum, you mean?
Yeah.
So from the spectrum, you can get the composite ones. So if the hot subdwarf in binary systems with the FGK type, so what you get is a spectrum of STB with FGK type. So you can do some then disentangling. So then you can derive the T effective and log G for hot subdwarf or the main sequence companion. You can get that information from the spectroscopy.
And have you noticed any chemical peculiarities?
Yes, we have around, I think, yeah. So let me tell you the exact number. So in the case of volume-limited sample, we have 48 of them. So just the spectrum that we looked at. So that, or when you build a spectral energy distribution, you see infrared excess. In the case of you have, for example, F type of main sequence companion. Another insight from the spectrum, you can get Zeeman splitting that indicates the magnetic field, strong magnetic field. And we have just 2 or 3 objects. So STB is mostly magnetically poor objects.
My second question, yeah, we can actually stick to this diagram. I'm actually curious, I mean, this is maybe naive. What is the effect of variability in this diagram, for example?
Type of variability?
No, effect of it.
Sorry.
Do you expect any effect of your pulsations on this exact diagram? Because this also then affects your mass derivation, etc., everything, right?
Yeah, so basically, what I'm focusing on concerning the pulsations between 20 to 40,000 Kelvin. So this region, right, the blue shaded area, where you can find the pulsating ones, either short period pressure mode pulsating ones or long period G mode ones. And yeah, but not all the stars within instability strip are not pulsating, right? And this is another open question, for example. And yeah.
Okay, thank you.
Yeah, you're welcome. And concerning SDOs, it's also a few pulsating candidates we have, so not much.
If I got Shriya's question right, I think the question was, TF and log G come from spectroscopic analysis. What is the potential effect of stellar oscillations on line profiles, and how this diagram could potentially be perturbed by the effect of pulsations on the spectrum?
That's a great question. I'm not quite sure the answer, but the stellar oscillations, I think, wouldn't affect too much to the what you get from the spectrum, like in terms of log G and most of them, yes, just one.
Yeah, so I would expect some line profile variations over your whole pulsation cycle.
But keep in your mind that it's the just 12% of them are pulsating. Okay. So if there is an end effect, just 12% would be distorted in this diagram, if any. But,
okay. Thank you.
Yeah.
More questions? Well, people are thinking I'll go to Connie. She will surely have a question.
Hi, Murat, thanks. I have a very practical question as a seismologist, because all your compact stars are in a very easy regime in terms of rotation and magnetism, in the sense that these are perturbative effects, so easy to deal with theoretically. My question is anybody doing frequency inversion, because you also have all the modes identified, and this is the way to find out what is wrong in your model. So as far as I'm aware, people only do forward modeling, but this would be a prototypical case where inverse modeling would be so much better. Is anybody doing that?
I don't think so, if anybody is doing it.
That's what I would do.
Hi, I also have a couple of questions. They are mainly connected to your DZ white dwarfs, so the heavier element detections. Yeah, these ones. So are these also all binaries, or they are not connected to binaries at all?
Binary is difficult to determine in the case of white dwarfs, especially from the spectroscopic point of view, because as you can see here, the lines are quite...
so these are single white dwarfs?
We don't know if they are single or in binary systems.
Okay.
So we don't know. But in the case of these objects, yeah, it's specific that the equation should come from the external sources.
Yeah, yeah. And so you also mentioned the planetary accretion, planetary material accretion, right? So this is also, some of us call it white dwarf pollution. And indeed, it has been associated to planetary material. But do you know of any other theories of how this could be? Could it be not planetary material? Do you know of? So this is more of a general question.
I see. I think this cannot be originated from the interstellar medium that we already excluded. And this can only be formed through the planetary remnant around white dwarf. So basically, what is remained is already destroyed and accreted into the white dwarf. And the people already start to work on what would be the planetary composition in main sequence using these stars. So they are really good tracer.
Yeah.
And another important point is that what we know from the exoplanetary science is we don't know much about the exoplanet characteristic around intermediate mass stars, right? FGK. And current white dwarfs came from there. So if you find any material, so then you can also go through the main sequence. So you can get some answer, because the radial velocity in that range in the main sequence is not working pretty well, right?
Yeah. And for this DZ category, the Z is for you like greater than oxygen, or like carbon, oxygen?
Any type of a heavy element.
So anything like heavier than helium for you classifies as DZ?
Yeah,
okay. Thanks.
So I have an answer to Connie's question. Is Stephen Chabonnet has a paper on the inversion. He found differential rotation with almost solid, but a little bit of differential rotation. So a question to Murat. So you have a slide showing the rotation splitting. There's a L equals 1. You can see the L equals 1 splitting. The left spacing is less than the right spacing. It's probably the second order Coriolis effect for GMOs. I guess so.
I think so, yeah.
Yeah, I'm just wondering whether anybody has checked the splitting of symmetry in SDB stars. Or
I think from the rotation multiplets, no. But nonlinear mod coupling and this type of amplitude modulations, frequency modulations, and phase modulations already studied. But what you talked about, as far as I know, no.
You just a symmetry for the last L equals 1 triplet. I guess a symmetry because the left spacing is less than right spacing. This is the signature of the second order Coriolis effect for GMOs.
Yeah. Well, great to know. Actually, you should model.
Yeah, I'd be interested to check that. Now, the second question is, in a lot of the SDB stars, we see the buoyancy glitch, the glitch in the period spacing pattern. You have these wiggles.
Yeah.
I mean the glitch. I'm just wondering. I have seen a lot of papers on the G mode glitch on the period spacing and the Echelle diagram. But does anyone has seen the P mode glitch, like acoustic glitch for the SDB stars?
No, because in P mode region, this asymptotic period spacing wouldn't work. Those modes are not equally spaced in period.
Yes, yeah. I mean, there are P mode pulsating SDBs. I'm just wondering whether we have some glitch signatures.
No, because it's just know that a few reach pulsating P mode pulsators.
Oh yeah, okay. Thank you.
But I didn't see any glitch pattern for those.
Thanks for this nice talk, Murat. I have a question. So in the very beginning, you showed this beautiful plot from Gaia that has all the white dwarfs. And one of the things that I remember when I saw one of these talks coming out from the DR2 was the splitting of your white dwarf sequence into two. I found that really interesting, but I have no idea really what that means for pulsations.
Oh, that's a great question. I didn't touch on that. So Gaia was like revolutionary for white dwarf people, because they recognize that there is a bifurcation, so which indicates that not all the white dwarfs cooling at the same pace. So which was the new information from Gaia? Because previous studies, as far as I know, they all, by the time they cool in a similar pace concerning different objects. But Gaia shows that it's not the case, because some objects are just stop the cooling. So, and they associated with the potential mechanism have been proposed, one of the paper, and it claims that it's perhaps there is a phase separation for those objects. So liquid to crystallized white dwarf. So that phase separation perhaps responsible for this cooling delay, as far as I know.
Yeah, and so the ones that crystallize, would you expect any pulsation from those? I'm just wondering, is there one of these edges that are just not showing pulsations?
Yes.
Just because the internal structure is
yeah,
so
actually
different?
One of the cases I showed you, actually two of them. So these are like, if you believe the models, these are like 99% has crystallized core. That's what the model shows, based on these pulsations, 13 significant pulsations. So we did a period-to-period matching using the model. And of course, we have only available model for, in the case of these stars, oxygen and neon core. So there are assumptions. So that might not be the case. Perhaps this star is composed by carbon and oxygen. That's the first cavity. But if you believe this star is composed by oxygen and neon, and the period match is correct, so then what you have is 99% crystallization on the core.
Okay, thanks.
Any more questions? Murat, if you could go to your slide where you compared masses, seismic masses with spectroscopic masses. So you seem to be concerned with the scatter, so that's the top left plot there. So the scatter above about like 0.7 solar mass or something like that.
Yeah.
And you use that as an argument to say like, well, there is a problem with our atmosphere models and or seismic model stuff. But can you really conclude on that? Because scatter does not worry me. I would be much more worried by some systematic effect. So your individual uncertainties are probably somewhat underestimated. They are pure statistical errors. So why does the scatter bother you so much there?
Because, I mean, there are many stars is located in this region, right? So it seems that, and let's just focus on this residual plot. This is a blonde Altman diagram. So there is now any scatter here, up to 0.75, as you can see here. But beyond that, there are scatter. It started. And one of the things is that if you just follow the, so by the way, I forgot to tell you that the size of the symbol just correspond to number of pulsations. So if the symbol size is bigger, so you have more pulsational frequencies, so better modeling. So if the symbol size is smaller, so which means that you have just a few peaks, so the model perhaps suffer to match. And in that case, if you look at the upper side, and the number of pulsational frequencies decrease significantly, that might be another issue.
Mm-hmm. And can you enlighten me on how the spectroscopic mass is derived for these objects, and to what extent, if at all, does it depend on RV measurements?
So spectroscopic mass is calculated. First, we obtain the low resolution spectrum. So then we derive the log G and the T effective. So using the evolutionary tracks, we determine the mass of the white dwarf, basically.
And that is spectroscopic mass, you call it?
Yeah.
Okay, I would call it rather an evolutionary model, but okay.
Evolutionary model, or we called in this spectral.
Okay. Okay. We still have time for one more question. No? Then the last one from me. For your period spacing pattern, where you have this wiggly structure, right? So you seem to be very much convinced that this is physics there, but looking at your periodogram and how, let's say, messy it is, a bit, to lower or higher frequency, you could actually make it a straight line. To what extent this wiggly pattern could potentially be just a methodological effect?
Yeah, that's a great point. In this case, I cannot assure you that, because this data is from TESS. But in the case of Kepler, yes, I can show you really clear pattern, because Kepler observed during 4 years, and we have a rotational multiples to identify the degree of the mode. So then, using this method, we can say that this is definitely equals 1. So then we build again the similar diagram, and then you see that wiggle shape, and even most of the cases you can see also trap modes.
Okay.
But concerning this data set, yeah, you're right.
Yeah, thanks a lot.
Thank you.
We are at the hour almost. Let's thank our speaker again. Thanks for coming, and see you next week.